Let's do another example. Let's find characteristic equation and the eigenvalues of this matrix. Okay, 5, 0, 0, 0, negative 2, 3, 0, 0, 6, negative 8, 5, 0, and negative 1, 0, 4, 1. Okay, so I want to point out that this is actually a triangular matrix, so you already know what the eigenvalues are. They appear on the diagonal. Let's write down the characteristic equation anyway. Okay. Okay, so the determinant of A minus lambda times the identity is equal to the determinant of subtracting lambda times the identity is going to be subtracting lambda from each of the diagonal coordinates. This will be 5 minus lambda, 3 minus lambda, 5 minus lambda, and 1 minus lambda. And everything else stays the same. I got negative 2, I got 6 and negative 8, I got negative 1, 0, and 4, and I got zeros everywhere else. Okay, to find the determinant of this matrix, I would just multiply down the diagonal, because if you do a cofactor expansion, you go down the first column, you have this term. This is equal to 5 minus lambda times the determinant of this submatrix. Let's go down this row again. 3 minus lambda times another 5 minus lambda and 1 minus lambda. Okay? So what I want to do now is set determinant of A minus lambda times the identity equal to 0. So this is the characteristic equation. Right? And this here is a polynomial. Okay, you see that we don't have to factor because the polynomial is already factored. Okay, so if I'm setting this equal to 0, I have 5 minus lambda squared, because I have two factors of 5 minus lambda, and then 3 minus lambda and 1 minus lambda equals 0. So I get that lambda has to equal 5, 3, and 1. Okay, what I want to do now is define the multiplicity of an eigenvalue. So multiplicity has a meaning in regular algebra, not linear algebra, as just the number of times that a root is repeated in a polynomial. Okay, so the powers on the roots, when you've got the polynomial factor, tell you the multiplicity. So here's a power of 1, and here's also a power of 1. So in this example, the eigenvalue 5 has multiplicity 2, and that just comes from this power. The multiplicity of the eigenvalue 3 is 1, and that comes from this power, and the multiplicity of 1 is also 1. Okay, the importance of multiplicity of eigenvalues actually shows up in this theorem, which comes from section 5.1. Let me say theorem. So if I have a set of vectors that are eigenvectors, so what do I mean by distinct? What I mean is that they're all different, which means in this, by this definition up here, the multiplicity 1. Okay, there are no repeated eigenvalues. Then what I get is that V1 and V all the way to VR is a linearly independent set. Okay, and the proof of this is in section 5.1. So you can check it out if you like. It's a little bit technical, but you know that linear independence is an important topic in this class. So if I have all my eigenvalues multiplicity 1 in my characteristic polynomial, then the corresponding eigenvectors are all linearly independent, which we'll use later when we're talking about diagonalization.